Hi, I'm Chung-Lin Chan and I'm Group 23 and today my simulation topic is mainline headway and braking distance simulation with heterogeneous train traffic. And this is my today's outline. And what drives me interested in this topic is because train compared to car, it has a very low fraction rate. So actually it can takes 30 times longer distance to break down. That means a lot of factors easily to affect the final result of the braking distance, and that makes me interested to using the simulation tool to doing this analysis. So how to determine the brake distance? Uh, Actually, it is not accurate to directly calculate by formula, since in reality there's so many factors that will influence the braking distance during their process, such as track rate, curve, and wind speed. So it is good to run simulations to get answers. And in this final project, I run the Monte Carlo simulations. So with a given route, and there are a lot of starting points, and for each point, I will run hundreds and thousands of times to determine the reliable result of braking distance at each point. And we're discussing about two types of train, the passenger train and the freight train. And if we given only one type of train on the route, then it is homogeneous. But if there's a mixed type of passenger train and freight train on the route, then it is heterogeneous train. And this will generate a different output of the headway. The headway is determined by the train length, braking distance, and its speed. So uh, if we have information of headway, we can use it to evaluate the route's capacity and efficiency. So the lowest the highway value is, then you can departure more train in a given time. That is more efficient. So in our supporting data, it is a 200-mile lane network from a certain class 1 railroad, and for these 200 miles we have curve, grade, and speed informations, and I will simulate at each milepost. That it means every mile I will do a simulation. So these are the given data. Like this is the speed restrictions, and this is the grade change, and this is the curve change. And I make several assumptions. First of all, I fix the value and the weight of the freight train and the passenger train. So I assume they are identical respectively. And I use a speed reduced interval with 5 miles per hour. And for the raw data, each starting point I run 1,000 times. And how to determine the braking distance? I use the following formula. And this is an example like how I get the braking distance. Like once the train decrease 5 miles per hour, I will get a value, and until it decelerate to 0, and I will sum those lengths up, and that is the braking distance. And braking distance actually is affected by the brake force and the resistance. And today, I will fix the brake value for each type of train and mainly discuss about the resistance, since resistance is easily affected during the process, the train braking. So this is for the brake force type. So as you can see, I'll give the fixed value for freight trains and passenger train respectively. And then how to count the resistance of a train It's called a modified Davis equation. So this formula actually is affected by the train speed, train curve, train grade, train and the wind, and the train weight. So the headway calculation is depending on the braking distance, train length, and the speed. And if it's a heterogeneous traffic route, then the headway equals to the max number of the certain type of the train. So this is my model. First of all, this is a cycle using to brake. So once it reduces to 0 from a certain speed, this iteration completes. And this is the cycles I run for each starting point. So default I run 1000 times, but we will discuss the effect if I change the n value. And start means I start at a certain milepost, so it is ranging from 1 to 200. And rand is I set a random number to set up the error terms of speed and also the wind speed. And I run the procedure until it stops. So after I do the calculation, I get the braking distance of the freight train is like this. So through the 200 mile, sometimes it needs a longer distance to stop. However, sometimes it takes shorter. And also, since every milepost I run 1000 times, so I will get an confidence interval with 95% confidence. So with this orange area means we expect the real braking distance will fall in this area. And then I use the formula to count the headway. And as you can see, we can see through all the routes, the largest varies through the route is around 3.6. That means at this route, we can depart a freight train every 3.6 minutes. And this is the similar result for the passenger train, but you can see the braking distance is usually shorter. And this is the confidence interval. And for the headway part, you can also see it is also given a shorter headway. That means for this max result, I can depart a train up to around 1 minute. So every minute I'm able to depart a passenger train. And then finally, I discuss the effect of the n cycles I run. So for each point, if I try to run only 10 times, then I will get a very high standard deviation. However, if I gradually increase the cycles, I did 10, 50, 100, 500, 1000, and 10,000 at a certain starting points. And I found that once it reaches n cycles equals to 100, it will become stable. That somehow meets the theorem of the central limit theorems. In conclusion, we find that the headway of passenger train is shorter. In the heterogeneous network, it will somehow waste the capacity efficiency. And the trade-off capacity and the capital cost is you need to pay more if you want to do dedicate line, but the capacity is also higher. And when n larger than 100, it becomes stable. And this is my presentation. Thank you very much.